Hi, good morning. Today we are going to discuss about um, the concept of convolution and how we can use the concept of convolution in Laplace transforms and to find the inverse Laplace transforms. So we start with the concept of convolution. So let us have a function f of t, which has a Laplace transform f of s, and another function g of t with Laplace transform, say capital G of s. Now, the convolution of these two functions s of t and g of t is defined as integral 0 to t f of t minus u into g of u du, or is exactly same as integral 0 to t f of t into g of t minus f of u into g of t minus u du, and it is represented as f star g of t, or this is same as g star f of t. So it is a uh, commutative operation of two functions. Now, how it is related to the Laplace transform? So, if you calculate the Laplace transform of convolution of two functions, then it is nothing but the product of Laplace transforms of the two functions. Or, in other words, this is equal to f of s into g of capital G of s. Then the main application of this particular result is to find the inverse Laplace transform of product of two functions like f of s into g of s. That is, inverse Laplace transform is the convolution of uh, uh, f of t minus u into g of u d. So we can use this result to find uh, the inverse Laplace transform of product of two Laplace transforms. This is equal to the L inverse of f of s convolution L inverse of g of s, or it is f of t convolution. Now let us illustrate this concept using a few examples. Let us start with find the inverse Laplace transform of s square divided by s square plus a square the whole square, which is equal to the inverse Laplace transform of s square by s square plus a square into s by s square plus a square, like this, s by s square plus a square into s by s square plus, and we know that s by s square plus a square is the Laplace transform of a cos a t. So here it is a product of two Laplace transforms, and we can write it as like this L inverse of s by s square plus a square convolution L inverse of s by s square plus s square. Step can be skipped and is equal to cos at, the convolution cos at, and so then we use the definition of convolution. It is integral 0 to t cos of a into t minus u into cos of a into u du. U is the variable of integration here, and this is equal to integral 0 to t. It is softer form, um, cos a cos b, and cos a cos b is uh, equal to cos of a plus b, that is at plus minus au plus au, uh, cos a plus b uh, plus cos a minus b, that is at minus au uh, minus au uh, all divided by 2. That 2 is taken outside here. Cos a plus b uh, plus cos a minus b uh, du. Du is the variable of integration here. And now it's equal to 1 by 2 into integral 0 to t. This cos at get cancelled, and what remains is au plus um, here 1 minute, it is cos at minus au plus au, so it is not at, this is au. So while simplifying, here is minus au and plus au get cancelled, and this is cos at plus cos of at minus 2au d. Now what remains is the integration. So it is integral cos at, the integral is sin at divided by a, then in between 0 and t, plus here it is sin at minus 2au divided by, we are integrating with respect to u, and therefore this minus 2a in between 0 and t is equal to 1 by 2 into upper limit, it is uh, okay, there's a small problem here. The variable of integration is not t, it is u. So what we get here is not sin at, it is cos at. There is a constant as far as the variable of integration u is concerned, and the integral of u is du. Integral of du is u, and u in between 0 and t. So this is equal to 1 by 2 into cos at into u in between 0 and t. Upper bound is t, lower bound 0. Then plus here the upper bound, it is at minus 2at, that is sin at minus 2at, that is minus at uh, divided by 2a minus 2a, then minus lower limit u is equal to 0, so it becomes sin at divided by minus 2. Then just simplify these terms, and we have 1 by 2 into cos at into t. Uh, we can take this minus 1 by 2a as a common factor, and what remains is minus sin at, and here we have minus sin at. So sin of minus theta is minus sin theta, so it is minus sin at minus sin at minus 2 sin at. Then we can simplify one more step. It is 1 by 2 into t cos at. Then this minus can take outside, so it becomes plus. 2 and 2 get cancelled, so it is 1 by a sin at. So this is the required inverse Laplace transform of functions. Consider another function. Let's find out the inverse Laplace transform of 1 by s plus 1 into s minus 1 the square. So the straightforward method is to use the method of partial fractions and find it as or express it as a by s plus 1 into b by s minus 1 into c by s minus 1 square, and find the values of a, b and c, and then the inverse Laplace transform of 1 by s plus 1, 1 by s minus 1 and 1 by s minus 1 square. They are all known, and we can obtain the Laplace inverse of each and every compound. So that is straightforward method, and anyhow we are just going to use the inverse convolution theorem to find the inverse of this particular function, and for that it is L inverse of 1 by s plus 1, it is taken as one function, and uh, convolution, the inverse Laplace transform of 1 by s minus 1 the square, and this is equal to the convolution of two functions. The first one is the inverse Laplace transform of 1 by s plus 1, which is e raised to minus t, and the second function is the inverse Laplace transform of 1 by s minus 1 square. So by shifting theorem, it is e raised to t into 1 by s square is Laplace transform of t. So t e raised to t. Then by definition, it is integral 0 to t. We take e raised to minus t as the first function. So e raised to minus t minus u into e raised to u into u d. It is equal to when we expand the first e raised to minus of t minus u, we get integral 0 to t e raised to minus t into e raised to minus of minus, that is plus u, into e raised to u into u d. So since we are integrating with respect to u, e raised to minus t is a constant that is taken outside. Then what remains is integral 0 to t u into e raised to 2u du. Now just integrating e raised to minus t into first function into integral of the uh, second minus integral of derivative of the first into integral of the second d, which is equal to e raised to minus t into applying the upper limit and lower limit here. Lower limit when u is equal to 0, this time will vanish, and the upper limit we have t e raised to 2 into t divided by 2 minus here again we have to integrate one more time, so it is integral of e raised to 2u is e raised to 2u divided by 2, so 2 into 2 is 4 in between 0 and t, and this is equal to e raised to minus t into uh, t e raised to 2 into t divided by 2 minus the upper limit is e to the power 2t divided by 4. Then lower limit is minus, and here we have another minus, so it is plus uh, e raised to 0, that is 1 divided by 4. Now we can multiply with e raised to minus t, and we got a simple form as t e raised to t divided by 2 minus e raised to t divided by 4 plus e raised to minus t divided by 4. So this is the required inverse Laplace transform of our given function. The same can be obtained using the method of partial fractions. So what I advise is to find uh, the inverse Laplace transform of 1 by s plus 1 into s minus 1 the square using the concept of partial fractions. So this method, this is to be uh, considered as a follow-up activity. Now, now consider L inverse of 1 by s square plus s square into s square plus a square, which can be written as the product of two functions 1 by s square into 1 by s square plus a square. This 1 by s square is the Laplace transform of t, and 1 by s square plus a square is the inverse Laplace transform of sine at divided by a. So this is equal to uh, the convolution of two functions. One is t and other one is sine at divided by a. And by definition, this is equal to integral 0 to t. We take t as the first function, so it is t minus u into sine a u by a du. That a is a constant, so it is taken outside the integral. And this is equal to 1 by a into 1 by a into integral 0 to t uh, t minus u into sine au du, and this term here, this integral can be evaluated using integration by parts, and that is equal to 1 by a into first function into integral of second, that is sine au. The integral is cos minus cos au divided by a, so it is minus cos au divided by a in between 0 and t minus integral of derivative of the first with respect to u, that is minus 1, into integral of the second, that is sine au, that is cos au, so minus n also, divided by a, and here we have a minus sign b. Now this is equal to, here we have 1 by a into uh, upper limit and lower limit. Upper limit u is equal to t, so t minus t that equal to 0, so this value is equal to 0. Then in the lower bound, when u is equal to 0, what we have is uh, t minus 0 into upper limit is 0, lower limit so minus of minus plus, and cos a into 0 divided by a minus, here this minus and minus get cancelled, and what remains is the integral of cos au, that is sine au divided by a. There's an already an a, so it is a square in between 0 and t, and is equal to cos 0 is 1, so it is 1 by a into, here it is t by a minus the upper limit is sine at, and the lower limit is sine 0 divided by a square, and this is equal to 1 by a into this is t by a minus sine 0 is 0. So what remains is sine a t divided by a square. So this is equal to, if we take an a square outside, then 1 by a cube into a t minus sine a t. So this is our uh, function. So the what we have here is L inverse of uh, 1 by a square into a square plus a square is equal to 1 by a cube into a t minus sine a t. So that's a method by which we use the convolution theorem to find the inverse Laplace transforms. And I strongly recommend to familiarize this method by solving a number of problems. And in our next class, uh, we are going to some applications of Laplace transforms. So Laplace transforms are mainly used to solve differential equations, and um, in our next session we are going to discuss it. And till then, just thank you.